A All right, there you go. Good morning, everyone. Thank you so much for being here today. I hope you're all keeping well and staying safe. My name is William Blanzeisky. I am a PhD student at University College Dublin, Ireland, and I'm working under the supervision with Dr. Park Cunningham. And in the time that I've been given today, I would like to talk about algorithmic factors influencing bias in machine learning. It is fair to say that many of the prominent examples of bias in machine learning arise from bias that is there in the training data. And in fact, some would even argue that supervised machine learning algorithms cannot be biased. In today's presentation, I would like to illustrate how, in the absence of intentional interventions, a trained machine learning model can introduce or at least exacerbate undesirable biases in the training data through underestimation. Before we dive in, let's first introduce what is termed as algorithmic bias. So in general, a machine learning model is considered fair if it's not inclined to award desirable outcomes to only one side of the sensitive category. And desirable outcomes here could be whether or not someone is given the loan or whether or not someone is given the job, while as the sensitive category could be gender or race. And in this paper, we classify two main sources of bias. Bias due to the data, or sometimes referred to as negative legacy, and bias due to the algorithm itself, or underestimation. Negative legacy occurs could happen due to labeling errors or poor sampling, but it is likely to reflect discriminatory practices in the past. When the focus is on bias due to the algorithm itself, underestimation happens when the algorithm focuses on the strong signals in the data, thereby missing more subtle phenomena. And our hypothesis is that underestimation occurs when an algorithm underfits the training data due to a combination of limitations in the training data and model capacity issues. Despite knowing for a fact that various kinds of biases can creep into any stages in machine learning pipeline, a rather prevalent belief is that a machine learning model merely reflects existing bias in the data set and does not itself contribute to harm. However, a recent work has shown that the algorithm itself could amplify existing bias. And of particular interest in this regard is research on model pruning in deep neural networks. Since the 1990s, there has been research on how a significant proportion of weights in neural networks could be pruned with a minimal loss of accuracy. Recent work at Google Brain by Hooker et al. Shows that model pruning in deep neural network can indeed have a significant impact on bias amplification. And further research on underestimation also shows that measures to address overfitting in machine learning training can accentuate bias. And with that being said, the goal of today's presentation is to emphasize the need for understanding the role that both the data and the algorithm in contributing to bias. And we believe that a more informed understanding of what contributes to algorithmic bias is important because it also dictates where we spend effort mitigating these harms. And thus, recognizing how algorithmic factors in machine learning training impacts these harm could open up discussions on remediation strategies that are less burdensome than a comprehensive data collection. So let's now move on to quantify these type of biases. Disparate impact is one of the accepted definitions of unfairness, and it is defined as the ratio of desirable outcomes predicted for the sensitive minority compared with that for the majority. When the focus is on bias due to the algorithm, we can then define underestimation in line with the disparate impact as the ratio of desirable outcomes predicted by the classifier for the sensitive minority compared with what is actually present in the data. So basically, if the US score is less than 1, it means that the classifier is under predicting desirable outcomes for the minority. It is also important to note that US score of 1 does not necessarily mean that the classifier is not biased against the minority group. Because, for example, there could still be evidence of negative legacies like a poor disparate impact score. An alternative to this underestimation score we define is the one used by Kimishima that considers the divergences between the overall actual and predicted distribution for all groups based on the Hellinger distance. So in other words, this notion kind of quantifies to what extent a model's predictions deviates from the data in which the model is being trained on. And so UEI's underestimation index of 0 would indicate that there is no difference between the probability distributions of the training samples and the prediction made by the classifier. But for the rest of the presentation, we will be basing our evaluations using the underestimation score we defined earlier rather than this UEI index, because it focuses on the impact on the sensitive minority in the same way that the disparate impact score does. And we also found that the UEI index could sometimes hide detail because it is an aggregation score across all feature and outcome combinations. It is also worth emphasizing the distinction between underestimation and classification bias. Classification bias occurs due to the model being trained on a highly imbalanced data set, resulting in predictions that underestimate the overall minority class. So we basically can refer to this as a underestimation at a class level. In contrast, the underestimation score defined earlier reveals situation where this underrepresentation is intensified for a specific sensitive group. And to highlight this distinction, we evaluate the predictions of several classifiers in terms of underestimation score on a fairly simple synthetic data set. And we can see here that in almost all cases, the classifier underestimates the overall class labels. But then we can also see that this underrepresentation is exacerbated for the minority features for the protected group, and in most cases, it is being overestimated for the unprotected group. And we believe that there are 4 factors that contribute to this underestimation. The first one being irreducible error, or sometimes referred to as base error rate. In supervised machine learning, the assumption is that the outcome variable y is determined by the inputs to the model. But typically, the inputs do not completely determine the outcome. So even the best model will still have some error. So when the irreducible error is low, the best model will still be able to fit well to the training data and still generalize well to unseen data. But on the other hand, if the irreducible error is high, then models that can generalize well will need to be relatively simple, meaning that they would underfit the training data. And to illustrate the impact of irreducible error on underestimation, we perform an experiment on a synthetic data set. This data set has a clear evidence of negative legacy. It consists of 5,000 observations, with each observation represents an applicant statistics, which include IQ score, SET score, a sensitive attribute in this instant is gender, I believe, male and female, and the target variable admit indicates whether or not a student is admitted to the program. We then perturb the numeric independent variables with a Gaussian noise, and the rationale is that the more noise added, the higher the irreducible error gets. So the x-axis here represent the amount of noise added to the numeric independent variables. And we see that underestimation is indeed magnified when the irreducible error is high. So this supports our hypothesis presented earlier that high reducible error rate results in simpler model, which then result in bias accentuation for the minority class. Next, we explore how the use of regularization mechanism influences underestimation. It is usually a standard practice in machine learning to use regularization mechanism to reduce generalization error. And these methods are used to control the model capacity to gather relevant information from the training set. And the objective of ensuring that the model does not overfit or underfit this information is crucial in machine learning because it is tied to the model's ability to generalize well on unseen data. So excessive regularization will likely cause a model to underestimate predictions for the minority class. And for this, we consider 4 classifiers on scikit-learn that allows explicit control of the regularization applied. For example, here, like neural networks, it provides an alpha parameter that controls how much of the regularization is applied to the classifier. And these figures shows how underestimation varies with these parameters. And it is clear that underestimation is exacerbated as the strength of the regularization mechanism increases. This makes sense since higher regularization means that models' ability to learn from the data is restricted. And thus, when the observations for the minority group are already scarce, the model will tend to focus on the majority and resulting in underestimation for the minority group. Lastly, we explore how class and feature imbalance influence underestimation. This is one of the most common causes of bias in machine learning, and this difference in frequency often leads to disparate error rates on underrepresented groups. And these figures here show how sensitive underestimation is to the distribution variations in the class and in the feature labels. So as you can see here in the heat map, the class imbalance varies from 10% to 30%, while the feature incidence varies from 10 to 50. To achieve certain level of class imbalance and feature imbalance, we took a sample of the original synthetic data set that I mentioned earlier. And from this heat map, we can see that the color of the heat map gets darker towards the top left corner, indicating that underestimation is indeed accentuated when observations for the minority class is scarce and the categories are extremely underrepresented. So it is worth emphasizing that each value in the heat map represents the underestimation score for a specific class and feature imbalance. Now that we have discussed this, what factors influence underestimation, the important question would be, what can we do to alleviate this problem? As stated earlier, that underestimation occurs when the classifier underfits the data due to limitations in the training data and also model capacities issues. So the most straightforward approach to fix this problem is to gather more representative data, right? But quantifying exactly how much data is needed is not a trivial task in practice. So in this paper, we brainstorm a few ideas on what we can do to alleviate this problem, and these strategies could be categorized into 3 different categories: pre-processing, in-processing, and post-processing. The main idea behind the pre-processing strategies is to augment the data set and to transform the data sets to remove undesirable biases before we feed it into the machine learning algorithm. And this could involve data augmentations like oversampling technique, while as in-processing strategies explicitly uses underestimation as a criteria in model training, while as post-processing often transforming the predictions made by the classifier to remove undesirable biases. In this paper, we specifically evaluated a few pre-processing strategies, and the first one being SMOTE-F, and SMOTE is a well-known oversampling technique in the literature. So instead of the usual SMOTE strategy, usually balances the class labels in the data set. But then our variant of SMOTE, instead of just balancing the class labels, we also want to make sure that the feature imbalance is taken care of. So consider a job application settings here. If there are 60% of the applications are from male and 40% are from female, but then only 33% from the female that applied is awarded the desirable outcomes. We want to make sure that this underrepresented observations are balanced compared with that for the male ones, for example. So that is exactly what the SMOTE-F does. And the second strategy is by adding counterfactuals. So there are 2 options of adding counterfactuals to the data set in order to balance this underrepresented observations. And the first one being counterfactual L, and what counterfactual L does is that it converts, it flips the label. So we we oversample these minorities from the opposite label. So basically from female that is not awarded desirable outcomes, we took the sample of that and oversample it for the minority features. While as the counterfactual F, we do a feature flip. And so instead of oversampling it from female observations, we oversample it from the male observations. And the details of this algorithm is highlighted on the paper. And we do, and the important step here is to quantify how much counterfactuals or how much synthetic samples we should generate so that underestimation is not accentuated anymore. So we evaluate those strategies on one synthetic and two real data sets, and we found that there is no one-fits-all strategy. So basically, for example, counterfactual L performs well on recidivism data set, but it does not perform that well on the adult data set. So here are the results, but most of the strategies are did indeed help fix underestimation or bring underestimation closer to one compared with those without repair. So our current work is to utilize meta-heuristics to address underestimation bias in machine learning. So more of a in-processing strategies, and an early draft of the pseudo-simulated annealing technique to address underestimation is on arXiv right now. So feel free to check that out. And yeah, that is it for my presentation today. I'll be happy to take any questions I do.